Hi everyone, today's topic is Hall effect and we are going to derive Hall coefficient in terms of Hall voltage. What is Hall effect? When a current carrying conductor or a semiconductor is placed in a transverse magnetic field, an electrical field is developed in a direction that is normal to both current and the applied magnetic field. This phenomenon is said to be Hall effect, and the produced field is called as Hall field, and the developed voltage is called as Hall voltage. Consider a semiconductor. Let X, Y, Z be the three dimensions of the semiconductor. When it is applied with some current along the x-axis and it is placed in a way that it experiences magnetic field along the z-axis, then an electrical field will be produced in a direction perpendicular to both current and the applied magnetic field, that is along the y-axis. So along the x-axis current is applied, along the z-axis it experiences magnetic field, then a voltage is developed in a direction that is normal to both current and the applied magnetic field. Here electrical field is equal to potential drop per unit length or potential drop per unit thickness of the material. Since it is given as Hall effect, we are giving a subscript called as H by the name Hall. Now, Hall effect in N-type semiconductor. N-type is an extrinsic semiconductor. Here, the majority charge carriers are electrons and the minority charge carriers are holes. Consider an N-type semiconductor. Now, as per the explanation given for Hall effect, this N-type semiconductor, along the x-axis, current is allowed to pass through it. So it is moving from left to right along the x-axis. And the electrons in it, in this particular material, will be taking up the directional motion opposite to the applied field. That is, if current is applied in the semiconductor from left to right, electrons in it will be moving from right to left. Now, at this particular situation, it is experiencing an external magnetic field along the z direction. Then, since magnetic field is along the z direction, the electrons will be pushed downwards. So the electrons will be accumulating at the downward face. Thereby, a potential difference will be developed in a direction perpendicular to both current and the applied magnetic field. Since the electrons are pushed downwards, here along the negative y-axis or y direction, because this is positive y, the electrons will be producing a potential difference by moving downwards, negative y-axis. Therefore, along the negative y direction, this n-type semiconductor gives rise to a field called Hall field. So this is the theory. Now we are going to see the derivation part for the Hall coefficient. Now, force due to potential difference is, since it is a negative type of semiconductor, minus EH, and force due to the applied magnetic field, it is V minus EV, where V is the velocity of the electrons. Now, under thermal equilibrium condition, these two are equated. Minus EH is equal to V minus EV. So, minus E gets cancelled off on both the sides. We get EH is equal to B into V. Let this be equation number 1. So this velocity V can be taken from the current density formula. We know that current density is equal to, of a material is equal to, number of charge carriers and minus E with the velocity. If it is a metal, we know that J is equal to N minus E Vd. But here we are talking about semiconductor, therefore it is taken as N minus E V. Therefore V is equal to J by N E. Since we are talking about N-type semiconductor, the number of electrons is represented by Ne. Therefore, we have a minus sign here. Therefore, J divided by Nee. Substituting V from equation 2 in equation 1, we get EH is equal to V. This V is replaced by minus J by Nee, or B J minus 1 by Nee. This can also be written as EH is equal to B J RH, where RH is equal to minus 1 by Nee is called as Hall coefficient for an N-type semiconductor. Now, we are going to derive expression for Hall coefficient in terms of Hall voltage. So, we have 3 equations here. The third equation is EH is equal to BJ RH, where RH is minus 1 by Nee. Now, we know this formula. EH is equal to VH by L or VH by T. In this case, we are going to take VH by T. Therefore, EH is equal to VH divided by T. That is, electrical field is equal to potential difference or potential drop or voltage drop per unit thickness of this particular material. Therefore, VH is equal to EH into T. Now, substituting EH here, we get B J RH into T. Now J can be replaced by current density has another type of expression or formula, current per unit area, and here area can be taken as breadth into thickness of this material, breadth into thickness of the material. Therefore J is replaced by I by BT RH into D. So J is replaced by I by A is replaced with breadth into thickness, the area of cross section of the material. T, thickness get cancelled off. Therefore we get VH, voltage. This V represents voltage. This small v represents velocity. So VH is equal to V I by B into RH. So this is the expression for Hall voltage in terms of Hall coefficient, and if you want to express Hall coefficient in terms of Hall voltage, rearranging the above formula VH V by I B. So this is the required expression for Hall coefficient in terms of Hall voltage, where B is the breadth of the N-type semiconductor, and I is the applied current, and B is the applied magnetic field. Thank you.